Welcome to the lesson. We are going to talk about elasticity. Elasticity is a property of materials, and we are going to see how this behaves. This should be our learning outcome. We are going to demonstrate elasticity using springs and elastic rubber bands. Then compare the elasticity of two or more materials. Yes, so I said elasticity is a property of materials. So we are going to compare how they vary different materials. Then later on in the discussion, we are going to plot a force extension graph for some elastic material. That's when we apply a force to an elastic material, it extends. So you are going to see the behavior of the force that is applied compared to the extension, and eventually interpret what we see in the graph. We are very much familiar with this situation. If we should have a rubber band of this shape, we can stretch it and you see it will increase in length. Eventually, if you leave this applied force, it will come back to its original shape and size. What actually happened? So we applied a force to the rubber band and it stretched, thus it increased in length. The technical term for this behavior is actually deformation. So the rubber band will deform. So a simple deformation will be the stretching of it, increasing in length. Now, the behavior of the elasticity is that if you release the force that is being applied on the rubber band, then the rubber band will return to its original shape and then size. So here we are. After leaving it, it comes back. So from the original position, it stretches, and then it stretches upon the application of force, and then when the force is released, it returns to its original position. This is the behavior of an elastic material. Let's compare it in another way. Here we have another material that is not elastic. Let's suppose it is a piece of clay or a piece of glass. Now, if we try to apply forces at the ends, try to stretch this material, it will not extend and become longer. It will simply break. It will break. So such a material is inelastic. It is not an elastic material. So I've given you examples. We have a piece of clay that has been molded into this shape. Or it can be a piece of glass. So if you try to apply force, strong force enough, then instead of it stretching, it will rather break at a point. Now, if we should have a wire, a metallic wire, we can do the same thing to it. We can apply forces at the ends, and it will stretch. It will only break after you've applied so much force, but for a reasonable amount of force, it will stretch and then increase in length. You see, so it has some elastic property, some sort of elastic property in it. So we can have two materials that we are comparing: a piece of clay or glass compared to a piece of metallic wire. The piece of clay or glass is inelastic. It is not elastic. If you apply forces to its ends, instead of stretching, it will break at once. But for a piece of wire, it will stretch and increase in length before, if you apply excessive force, it will break or something. Alright. Now let's summarize what elasticity means. Materials that temporarily deform. We have a broad term called deformation, and a particular example is stretching the material. So if a material temporarily stretches or deforms on the application of forces, we can say that that material is elastic. Elastic materials will resume their original shape and size when the force that deforms them is removed. Now, some materials like glass and clay do not deform significantly. I'm saying they do not deform significantly because theoretically they will stretch slightly before they break. But in practice, in our common practice, like what we are learning about elasticity and deformation, we don't consider them as elastic at all, because the deformation that takes place before they deform is negligible, far negligible, very, very small. So we say they are inelastic in practice. So significantly, they do not deform, but break when force is applied to them. Okay, keep that point in mind. Now, materials will deform in different ways, or the elastic property of materials vary. Here we have two springs that I'm going to use to demonstrate. The two springs are hung on a clamp and they are hanging freely. The springs are spring A and then spring B. They are slightly different. Now we are going to hang the same mass. This is 200-gram mass. If this is mass, then you have to change it to kilogram, which is 0.2 kilograms. Yes, 0.2 kilograms. Then you multiply by the acceleration due to gravity, which is 10. It will make it at 2 Newton. Yeah. So we are going to have 2 Newton weights hang on this spring. The same 2 Newton weight is hung on this spring. But look, this one stretches more than the spring A. The spring B stretches more than spring B. So different materials have different behavior when it comes to elasticity. Some are more elastic, others are less elastic. So keep that point in mind. This is a typical example that I'm showing you. We have the same weight hung on two different springs, and one is stretching more than the other one. Alright. Now we can quantify elasticity and then try to understand the behavior of materials. We have what we call the force extension graph. This is another apparatus. This apparatus has only one spring on which different masses are hung. So if we go to the laboratory, we have this set of masses that we can vary the weight. Then we have a meter rule that is placed close by the spring, so that as it extends, we can determine the extension, how far it has increased in length. Alright. So for the same spring, when there is no mass hung on it, it has this length. If we hang just 50 grams or something on it, it will extend this far. Then if we hang about 100, two of these masses on it, it will extend further. If we keep on increasing the mass, it will extend further and further until a certain mass that permanently deform the spring. It will make the spring stretch permanently. It can no longer come back and become elastic again. So that will be our topic for next week when we discuss Hooke's law and then the elastic limits. But the point we want to raise here is that for the same spring or elastic material, if we increase the force, then the extension will also increase. Alright, so we can plot a graph for the amount of force against the extension. For the same apparatus, we have the spring, we have the meter rule by that side. The force that are going to be hung on this one, we call it the load, and it will be in Newton. Then the extension, this one is not just the extension, it's for the whole length of the spring. If we hook something on this one, we measure all the way from the spring to the final point where it extends. Then we can have a table. So when we put 1 Newton on it, it will extend to some point. Then when we have 2 Newton, it will extend to another point in that order. Then we can plot the graph. Alright, let me demonstrate that one with a simulation on the internet. Here we are. We have two springs. The two springs have different strength. This one is thicker. It's more stronger than the other one. Now I'm going to hook two masses, 250 grams and another 250 grams on this one. You can see that this one is stretching more than the other one. This is what I want to show you. This one is stretching more than the other one because this spring has different elasticity than the spring A. Alright. Now we can have just a single spring, and then we can see how they stretch. Okay. So this spring, when nothing is hanging on it, it will have no extension. So we place the extension at 0. Or in other words, we can place this ruler up here and start measuring. You can record this in your, in your portfolio, and then plot a graph for this experiment that we are doing, that you can see here. Okay. So we can start measuring from 0, that's from this point up to this point. So when there is no load at all, we have a length of the spring that is about 48 centimeters, like 48 millimeters. So it will be 48 millimeters. You can record that one when there is no load. Then let's hang a mass of about 50 on this one. This mass should be 50. So we have 50 here. We have 50 here. So you can see that it has extended from this point to this point. That is the tip from here. It has extended from here to that side. So here we are. If we have 50, it will extend to that point, about 60 millimeters. Let's increase the mass. If we increase the mass to, say, 100 grams, that's we double the mass. It will now go to 72. That's the length of the spring. Will now go to 72. Okay, then we increase it to, say, 150. And it will now go to 84.5. Yes, 84.5. Okay, let's increase it further to 200. When we go to 200, it's about 97. It's about 97. That's the point there. Yeah. So it is now 97. So we can go further and further, and if we have a longer ruler, we can measure the distance. So just use these 3 or 4 measurements, 4 values that you've had to plot a graph. To plot a graph for yourself. Okay, to demonstrate that you watch this video. Alright, so we can see that as we increase the mass or the weight, as we increase the mass, then the extension, the length of the spring also increases. So you need to keep in mind how this behavior comes about and the demonstration of it. Alright. Let me also remind you that you may need to change the mass to force. That's you convert it to kilogram and then multiply it by 10. That will give you, so for about 200 grams, it will be about 2 Newton. Alright, so do that then, and then we continue next week about that. Okay, so if you were to have a perfect values, then you are going to have something like this, which is a linear curve. Okay, so we have the load as horizontal axis, and then the extension as a vertical axis, because the extension depends on what load you hang on the spring. Okay, so you may have to you should be able to interpret this graph. Should be able to interpret this graph and then predict some other values. For example, for this particular graph, this graph is not from what we did here. It's not from this. It's an arbitrary value that I've given you from another experiment. So if we should remove all loads from the spring, what do you think will be the extension? Just looking at this graph, you can simply extend the line and then you can predict where the extension will be. That's the normal extension of the spring. Unloaded extension, that's the unloaded length of the spring. You can extend this one and then you can find where the length of the spring will be. Similarly, you can also ask yourself, if we should increase the load to about 6 Newton, then what will be the extension? What will be the final length of the spring? You simply have to extend the line to wherever it will get to and read the extension or read the length of the spring. Okay, so I'll give you more exercise on plotting graphs and then interpreting the graph. I'll give you, then you have to practice with them. Thank you.